Dam. The problem of filling a dam is used to show some of the essential features of the program in order to solve a hydromechanical coupled problem. No analytical solution exists for this problem. First of all, we are going to define geometry. Click on the Create Line icon and introduce the coordinates. A typical geometry of a dam consists of a core and the upstream and downstream slopes. Apart from this, in order to model the processes developed in the dam, a surface in the upstream side representing the water has to be drawn. Insert the coordinates of the geometry representing the water. Click the option Join when the last line is created, and now we have drawn the water geometry. Press Escape and repeat the same procedure to draw the geometry of the upstream slope, the core, and the downstream slope. Remember to always press the Join button when the option appears in order to close the existing geometry with the new one. I'll be inserting the coordinates of the core and the downstream slope now. You can skip this part. Once the geometry is finished, it's time to create the surface. Go to Geometry, Create, NURBS Surface, Automatic. Introduce 4 and press OK. This creates all the possible surfaces with 4 sides. The message "Created 4 new surfaces" appear. Now click Cancel, and we have the 4 surfaces created. Remember to save your work frequently, so if you have any problem, you will recover almost everything done. Now we are going to define attributes and conditions. First of all, sheet has to be customized for CodeBright. Go to Data, Problem tab, CodeBright. Now let's define problem data. Select Data, Problem Data, Problem Data. Enter all the general data that CodeBright needs to perform the simulation. Enter a title of the problem, for example dam. Then choose full execution. There is no symmetry, so select no in the axis symmetry option. Enter the value 0 for the gravity x and y component, and leave the default value in sheet gravity sheet. Now go to equation solve. Check the box stress of equilibrium. Choose no in the update Lagrangian method and check the mass balance of water option. Write 0 in the constant Pg field and 20 in the constant temp. In the solution strategy tab, put 1 in the epsilon and theta boxes. Introduce 1 in time step control, which means that the new time step is predicted according to the iteration number. Write 10 in the max number of iterations per time step. Choose direct LU bug 3 in the solver type and leave by default the average nodal degrees of saturation. Now set a value of 1 exponential minus 4 in max absolute displacement. Set a value of 1 exponential minus 8 in max node bulk forces. And set a value of 1 in displacement ether core. Now set a value of 1 exponential minus 3 in max of PL. Set a value of 1 exponential minus 8 in max node water mass bulk. And set 1 in PL ether core. Use the default option in the convergence criterion and let's go and fill the output tab. Choose all in the right numerical process information. Type 100 in writing the frequency, writing frequency. Choose use writing frequency in right boundary flows in additional file and choose Gauss points in the output points. Finally, tick the write all information option. Click accept to save the changes and close. Now we're going to define materials. Different materials make up this problem. Firstly, the dam per se consists of a core made of a low permeability material, the slopes, which consists of a rock fill, and in order to perform the simulation, we have to model the water as an independent material. Go to Data, Materials, and click on the New Material icon. Enter Core, click OK, and define the parameters defining the core properties. You can skip this part. I'm going to create the core, the rock fill, and the water materials. Edit material parameters. Save the changes and assign each material to the corresponding surface representing the core, the rock fill, the upstream and downstream slopes, and of course the water. You can skip the next 15 minutes of video. Once finished, you can click the draw button, all materials, in order to check you assigned them correctly. If everything is alright, click finish and then close. And we are going to define conditions now. As it is a hydromechanical problem, we are going to define mechanical boundary conditions, flux boundary conditions, initial unknowns, initial stress, and initial porosity. There are two mechanical boundary conditions. Select data conditions to define them. The first one is the restriction of vertical and horizontal displacement along the boundary y equal to 0. Select the line icon, select line force displacement boundary conditions from the drop-down menu, select boundary stress in the forces drop-down menu. The fields x displacement and y displacement must be set to 0, and the fields x direction prescribed and y direction prescribed must be set to 1. Assign this condition over the lines 1, 5, 8 and 11. You can label the lines going to view, level, all in, selecting the line icon, so you have all the lines labeled now. Click finish after selected, and let's enter the second condition, that's the restriction of horizontal displacement along the boundary x equal to 0. To do that, edit the y direction prescribed field to 0 and assign the condition over the line for the vertical boundary of the water. Click finish and click draw force displacement boundary condition in order to check the conditions assigned. Everything's alright, so click finish and let's enter the flux boundary conditions. In order to simulate the filling of the dam, a condition of mass inflow must be set at the base of the water. The line of the water's base allows for the water's injection. It's also necessary to set an impermeable base for the dam. Finally, a condition of seepage phase must be set in the downstream slope of the dam. To enter the mass inflow for a phase pressure prescribed at the line, press the line icon, select flux boundary conditions from the drop-down menu, select boundary flow rate in the flow rate menu, set 1 exponential 3 in the gamma for liquid field, and assign this condition over the line 1 at the base of the water. You can check that the condition has been assigned using the draw option. Now, to assign the impermeable condition at the base of the dam, select the line icon, choose flux boundary condition, select boundary flow rate from the flow rate field, and label the values to 0. Assign this condition over the base of the dam. These are lines 5, 8 and 11. This new condition creates a line of flux at the base made up by 3 lines of flux, which in other words set an impermeable base. To create a seepage phase in the downstream slope, in this same window set -1 exponential 6 in the gamma for liquid field. This negative sign only indicates that lines with these boundary conditions allows seepage, and assign this condition over the downstream slope. This is line 12. Click Finish and use the draw button to check the condition entered. If they are okay, continue with the initial unknowns. In this problem, there are two main initial unknowns. Firstly, it has to be taken into account that both the core and the rockfill are unsaturated materials. Therefore, a value for suction must be set for each one. Secondly, in order to model the filling of the dam, the atmospheric pressure must be set in the upstream side of the dam. To introduce initial unknowns, press the surface icon and choose Initial Unknowns in the pull-down menu. Select Constant in the pull-down button of Distribution. For the core of the dam, introduce minus 0.4 in the PL field and assign this condition over the core surface. Click Finish. And for the rockfill suction, use minus 0.2 and assign it over the upstream and downstream slopes. Finally, in order to set the atmospheric pressure in the upstream side of the dam, set the value minus 0.1 in the PL field and assign this condition to the surface making up the water. Now select Draw Colors to check if everything is assigned all right. Click Close. Let's introduce the initial stress. Press on the surface icon, choose Initial Stress, select Constant in the Distribution menu. Now set for the initial state stress for the dam minus 0.01 in the X, Y and Z stress fields and assign this condition to the whole dam. Now, in the same window, replace the values of the X, Y and Z stress fields with minus 0.001 in order to set the value of the initial stress for the water. Assign it over the water surface. To define the initial porosity, press the surface icon, select Initial Porosity and enter 0.3 in the porosity field. Assign it over the whole dam, that is the core and the rockfill, and introduce 0.9 and assign it over the surface materializing the water. This is necessary because the water is modeled as another material and it's necessary to set a high porosity value for this material. Enter entities, all materials, to check if every condition is entered. If everything is alright, click Close and let's define the interval data. By increasing the pressure in the boundary flux condition at the base of the dam, the filling of the dam is simulated. This is defined by two time intervals throughout 300 days. A preceding interval during which no load is performed must be set. This lets the system equilibrate the initial conditions. go to data, interval data, change the units of time discretization to days. Now define the initial time for the interval 1 as 0. The initial time step put 1 exponential minus 8. The final time 1.1 days. The partial time 0.01 days, and the partial time step the same. The box put displacement to 0 for the first time interval. Click accept and create a new time interval. Click yes on copy conditions from interval 1 and enter the next values. 1.1 for the initial time, 0.01 for the initial time step, 300 final time, 2 partial time, and 0.5 partial time step. Click accept. Once intervals are created, the pressure condition at the base of the water needs to be modified. Go to other options on the corner on the right, click on conditions and choose the line icon. Select flux boundary conditions, select entities, flux boundary conditions, click on entity E1. When selected, it is highlighted in blue, and click transfer. Close the entities window, introduce 0.47 in the prescribed liquid pressure increment and 1 exponential 8 in gamma for liquid field. Assign the modified condition to line 1. Check that the entity has been modified and return to the interval data window. After defining the interval data, we're going to define the mesh. In this example, a mesh composed by rectangular elements with a linear interpolation function and reduced integration is used. In consequence, the locking problem is avoided. Select Mesh, Structured Surfaces, Assign, and highlight the entire geometry. All the surfaces change from fuchsia to red. Press Escape and Enter Value window appear. Enter 10 and press Assign. Highlight the entire geometry again. This procedure creates tensils from the bottom to the top of the dam and water surfaces. All the lines and surfaces making up the geometry have to change from fuchsia to red. Press Escape and close the window. Now select Mesh, Structured Lines, Assign number of cells, and Enter Value window appears again. Introduce 4, press Assign and select the horizontal lines making up the water. This procedure creates 4 cells from the left side of the water to the upstream slope of the dam. Press Escape, the same window appears. Introduce 12, press Assign and select all the horizontal lines making up the dam. Press Escape and close the Enter Value window. Now generate the mesh. Go into Mesh, Generate Mesh. Click OK and a mesh generated window appears. Click View Mesh to view the mesh generated. Remember to save the work periodically. And now go to Calculate to process the problem. It will take a few minutes. and you can go to calculate view process info for a real-time description of the problem solving. In case any error appears, you will detect it. You can skip the next 8 minutes of the video, which is the program calculating, and go directly to the post process. Now calculation is done. Click the post-process button to access the post-process interface and view the results. Once post-process is initiated, all the materials are automatically colored. The variation of a result with time is an interesting feature. Go to Window, View Results, select a result. Well, first select contour fill from the View drop-down menu, then the result you are interested in, for example liquid saturation degree. Then select the step, in this case 300 days, and now go to Window, Animate. The Animate window will open up. Check the Automatic Limits box and press the play button. This will show a variation of the result with time. In this case, the liquid saturation degree, and you can appreciate the variation in the graph area. Here you can see which step is the animation showing, and if you right click on the image, you can select image to clipboard to copy the graph currently showing. Now close the Animate window, and it's possible to find the variation of a result with time in a specific point of the geometry. For example, of the Y displacement, if you want to see the variation in a specific point in the geometry, first select a Y displacement from the displacement result. Now press the right click in the graph area, go to Label, Select, and press the dot res icon. Now select a point in the middle of the curve, and the value for the Y displacement in that point in that step will appear as a label. If you go to the Animate option, you will see the variation of that value changing as every step changes. The evolution of plastic strains can be visualized. These are kept as a history variables for the viscoplasticity model used here. Selecting EDP for deviatoric plastic strain, here you can see the result, or EVP for volumetric plastic strain. Other interesting result for this problem is a variation of vertical stresses through the dam. Select stresses, SYY stresses, apply or double click, and you can also view the animation, which shows the variation of the vertical stresses through the time. Another interesting feature are graphs. For example, select liquid saturation degree result and go to View Results Graph, or to the graph icon, Line Graph icon, and select liquid saturation degree. Now draw a line selecting 2 points in the dam, for example from the top of the curve to the bottom. Once the second point is set, the graph appears. You can see the liquid saturation degree versus distance graph, and you can change the scale of the graph and set other graph preferences going to the Options tab. Let's uncheck the logarithmic scale in the x-axis. Oh well. If you wanna delete the graph, go to the clear option, that's the red cross, and click yes. That's all for this tutorial. To exit the program, go to File, Quit.